Welcome to this lecture on gas chromatography, or GC. In the previous lectures, we built the theoretical foundation and applied it to HPLC. Today, we will apply the same principles to GC, where the mobile phase is a gas rather than a liquid. This single difference has profound consequences for instrumentation, column design, and the types of analytes we can analyze. GC offers unmatched resolution and speed for volatile compounds. Let's explore how. We have 8 objectives today organized around the practical decisions a GC analyst makes. We start with carrier gas, move through sample introduction, columns, stationary phases, temperature programming, detectors, and finish with the Golai equation and retention indices. There are 3 worked examples and 6 practice problems. Here's the roadmap. GC versus HPLC, choosing the right technique. The fundamental question when choosing between GC and HPLC is, can the analyte survive vaporization? If yes, GC is almost always the better choice because capillary GC offers extraordinary resolution, often exceeding 100,000 theoretical plates on a 30-meter column. It is also faster and cheaper per sample than HPLC because the mobile phase is an inexpensive inert gas rather than the HPLC grade solvents. Look at the industry list on the right. If you work in petrochemicals, your primary separation tool is GC. If you work in environmental analysis, VOC analysis by EPA method 8260 is GC. In food and beverage, aroma profiling is GC. In forensics, blood alcohol is GC. Even in pharmaceuticals, which is dominated by HPLC, residual solvent analysis per ICH Q3C is done by GC. Understanding GC is essential regardless of which industry you enter. The GC instrument flow path is simpler than HPLC in some ways. No high-pressure pump, no degasser, no complex solvent mixing. The carrier gas flows from a pressurized cylinder through a flow controller into the inlet. The inlet vaporizes the liquid sample instantaneously at high temperature and sweeps it onto the column. Column sits inside a temperature programmable oven, which is a key difference from HPLC, where the column thermostat maintains a constant temperature. In GC, we systematically ramp the oven temperature to elute analytes of increasing boiling point. After the column, separated analytes reach the detector, which is maintained at a high temperature to prevent condensation. Let me walk through each component in detail. Carrier gas, the mobile phase of GC. The carrier gas in GC is analogous to the mobile phase in HPLC, but because it is a gas, it does not interact with analytes. Its only job is to carry analytes through the column. However, the choice of carrier gas profoundly affects efficiency through the Van Deemter equation. Look at the 3 curves. Nitrogen has the slowest diffusion, so its B term is small, and the curve minimum is at a low velocity of about 12 centimeters per second. But the curve rises very steeply to the right. If you run faster than optimal, efficiency degrades rapidly. Helium has faster diffusion, so the B term is larger, shifting the optimum to about 30 centimeters per second. The curve is flatter, meaning you can run above optimal without much penalty. Hydrogen has the fastest diffusion and the flattest curve. You can run at 50 or even 70 centimeters per second with minimal efficiency loss, which translates to much shorter runtimes. Helium is the standard in most GCMS laboratories because it is inert and capable or compatible with the mass spectrometer vacuum system. Hydrogen is increasingly popular for standalone GC because hydrogen generators eliminate the safety risk of stored compressed gas. Nitrogen is cheapest but gives the worst performance at high speeds. Injection techniques. Sample introduction in GC is more complex than in HPLC because the liquid sample must be vaporized. There are 3 main injection techniques. In split injection, the sample vaporizes in a heated liner, but most of the vapor is vented out through the split vent. Only 1 to 10% actually enters the column. This prevents column overload and is used for concentrated samples. The split ratio, typically 10 to 1 up to 100 to 1, controls how much enters the column. In splitless injection, the split vent is closed for 30 to 60 seconds after injection, allowing most of the vaporized sample to transfer onto the column. This maximizes sensitivity and is standard for trace analysis such as environmental pesticide methods. After the transfer period, the purge valve opens to sweep residual solvent from the liner. Solvent focusing at the head of the column helps reconcentrate the band. On-column injection deposits the liquid sample directly onto the column without vaporizing at first. This avoids thermal discrimination and decomposition and gives the most accurate quantitation, but it requires specialized hardware. Headspace and SPME, mentioned at the bottom, are sample preparation techniques that extract volatile analytes from the complex matrices like blood, food, or water without liquid-liquid extraction. Capillary versus packed columns. Modern GC is overwhelmingly done on open tubular capillary columns. These are thin fused silica tubes, typically 15 to 60 meters long and 0.25 millimeters in internal diameter, with a thin film of stationary phase coated on the inner wall. Because there's no packing material, the A term in the Van Demeter equation is zero. This is why capillary GC achieves such extraordinary plate counts. A 30-meter column routinely delivers over 100,000 theoretical plates. The trade-off is low sample capacity because the thin film has limited surface area. Overloading a capillary column causes peak fronting. WCOT columns with a stationary phase type or liquid stationary phase are the most common type. PLOT columns with a porous solid layer are used for separating permanent gases and very light hydrocarbons that are not retained by liquid phases. Packed columns are still used in a few specialized applications like permanent gas analysis, preparative scale separations, but they are essentially obsolete for routine analytical work. Stationary phase selection. Stationary phase selection in GC follows the like dissolves like principle, just as in HPLC. Non-polar analytes like hydrocarbons are best separated in non-polar phases like 100% PDMS. Polar analytes like alcohol is the single most popular GC column in the world. It handles an enormous range of analytes and is the default starting point for method development. The DB624 columns deserves special attention because it is the regulatory standard for residual solvent analysis under ICH Q3C. If you work in pharmaceutical manufacturing, you will use this column. The DB wax or equivalent PEG column is essential for flavor and aroma profiling in the food and beverage industry. Note that I have listed common trade names from multiple manufacturers. The same chemistry is available from all major vendors under different brand names. Temperature programming. Temperature programming is the GC equivalent of gradient dilution in HPLC. In isothermal mode, low boiling point compounds elute quickly and are well resolved, but high boiling compounds elute very slowly as broad, undetectable peaks. By ramping the oven temperature, you increase the vapor pressure of each analyte as its turn approaches, so it spends less time on the column and elutes as a sharp peak. The worked example shows a real method for residual solvent analysis under ICH Q3C, which is mandatory for pharmaceutical release testing. The method starts at 35 degrees to resolve dichloromethane, which boils at 40 degrees. A slow ramp to 85 degrees separates the other class 1 and 2 solvents. Then a faster ramp to 200 degrees elutes any high boiling residuals, and a 5-minute hold bakes the column clean for the next injection. The ramp rate matters. Faster ramp gives shorter run times but reduced resolution. Slower ramps give better separation but longer runs. A typical starting ramp rate is 10 degrees per minute. GC detectors. GC detectors are diverse because no single detector does everything well. The FID, flame ionization detector, is the workhorse. It burns organic compounds in a hydrogen-air flame and measures the resulting ion current. It responds to essentially any compound containing carbon and hydrogen bonds with a response directly proportional to the number of carbon atoms. It has an enormous linear range of 10 to the 7th power, which means it works well from trace samples. However, it does not detect water, carbon dioxide, thermal conductivity when an analyte passes through compared to pure carrier gas. It detects anything or detects everything, including permanent gases, making it essential for gas analysis. The ECD is extraordinarily sensitive to electronegative species like halogenated compounds. It can detect chlorinated pesticides at femtogram levels, 1,000 times more sensitive than FID for these compounds. This makes it indispensable for environmental monitoring of persistent organic pollutants. The Golai equation, van Deemter for capillary columns. The Golai equation is the capillary column equivalent of the van Deemter equation. The critical difference is that the A term vanishes because there are no packing particles. Only one flow path exists. This means the minimum plate height is lower than any packed column can achieve. The equation has two transfer terms, Cm for mobile phase mass transfer, which depends on the square of the column radius, and Cs for stationary phase mass transfer, which depends on the square of the film thickness. This gives us two important design features. Making the column narrower reduces Cm, making the film thinner reduces Cs. Both improve efficiency. The standard compromise is a 0.25 millimeter ID column with a 0.25 micrometer film. If you need higher capacity for concentrated samples, go to 0.32 or 0.35 millimeters, accepting some efficiency lost. If you need maximum efficiency for complex mixtures, go to 0.1 or 0.18 millimeters. Now for our worked example. As always, check the question, pause, try it yourself before we go through it together. We have a standard capillary column, 0.25 millimeter ID. 0.25 micrometer film, helium carrier with a representative retention factor of 5. The B term is simply 2 times dm, giving 0.6 centimeters squared per second. The Cm term calculation involves substituting column radius, retention factor, and dm into the formula. The key feature is that it depends on radius squared. Cs involves the film thickness squared. When you compare the two, Cm is about 8 times larger than Cs. This is typical. In capillary GC with thin films, mobile phase mass transfer dominates the C term. The optimal velocity comes out to 107 centimeters per second, which is enormously faster than HPLC's typical 2 to 3 centimeters per second. This is the direct consequence of fast gas phase diffusion. The minimum plate height is only 0.011 centimeters, giving 272,000 theoretical plates on a 30-meter column. Compare that to about 25,000 plates on a typical HPLC film. This extraordinary efficiency is why GC can separate very complex mixtures like petroleum products. Kovacs retention index. The Kovacs retention index solves a practical problem. Retention times are not reproducible between different instruments or laboratories because they depend on column length, film thickness, flow rate, and temperature. The retention index normalizes the retention of an unknown compound relative to a series of N-alkane standards that bracket it. By definition, N-decane has an index of 1000, N-undecane has 1100, and so on. An unknown that elutes between C10 and C11 will have an index between 1000 and 1100. In the worked example, the unknown has adjusted retention times that give an index of 1045 on a DB5 column. You can look this up in the NIST database or the Adams Essential Oil Library to identify the compound. Here, 1045 is consistent with limonene or beta-phenandrine, both monoterpene hydrocarbons. You would confirm the identity with mass spectrometry. Retention indices are particularly valuable in natural product analysis, flavor and fragrance chemistry, and environmental forensics where you routinely analyze complex mixtures of volatile compounds. Today's takeaways. We have 8 takeaways today, and you can see them. Please familiarize yourself with these. And here are the practice problems. Make sure to check them. Solutions will be posted. Thank you, and let me know if you have any questions.